All right, Andy, thank you very much for that very nice introduction. And let me screen share. All right, so my talk has, can everybody see the screen? I'm going to take that as a yes. So my talk has the immodest title, How Computing May Change Your World, Our World. What is going on here? 1 second. Okay. So what we're going to do is we're going to go into the background of where we're coming from. And what Amy didn't mention is I've been on the Computing Community Consortium prior to the CRA board for, I forget how many years, half dozen at least. And we're going to remind everyone how computing has and point out how it's going to continue to change our world. And 3 of the ways we're going to touch on are based on some CCC reports regarding artificial intelligence or machine learning, quantum computing, and computing in society. So all these, many of us are old enough to remember these things. If you don't remember a dial phone, at least you remember a landline. And these are still here, but we have many more computing things like the Zoom that we're on. I had an encyclopedia in my bedroom, and now everybody who has a computer has access to an encyclopedia. In fact, the model has totally changed. Encyclopedia is no longer authored by one person, but is authored by many, something that one might not think would work, but really does in many ways. And so this is an example where the technology changes things, and it even changes the business and creation model. Few of us are old enough that we used typewriters in college. Be thankful that when you made one mistake, you didn't have to use whiteout or retype the page because we had word processors such as this 1980s IBM PC. We still have postal mail sometimes, but it's been succeeded by email and a whole host of other social media platforms, for good or ill. This is a tremendous amount of change to our world. So why is computing so effective? From my biased point of view as a computer architecture researcher, I would argue that one of the reasons is universal hardware. And I'll say what I mean by that. It's one tool to solve many problems. So this is this 1980s PC again, but in many ways, this PC and your smartphone today are very close to each other. Just one's much faster and smaller. So what makes this computer so powerful? Well, the key thing is a separation between software and hardware. So what's software? Software is an algorithm. An algorithm is instructions to do something. So when you were in grade school, you were probably taught by some teachers how to do long division. So there's some rules for dividing any number to be named later by any other number to be named later to get a quotient. And you patiently remember these rules, and it's probably explained to you in English. Computers are dumber than you, and so when we have to give an algorithm to computers, we have to be very anal in our specification, and that's programming languages like C++ and Java. So you take this software, and we load this software onto this universal hardware, and now, among other things, this computer is now a divide machine. And wouldn't you like to have one, huh? And with a divide machine, you can give it some data, like A is 1200 and B is 50, and tell it to go, and out will come the quotient 24. And that's really what's happening. It's you loaded the software, you targeted this machine to this new use. And really, these applications that we talked about before are very complicated, versions of the divide algorithm. They're just much more complicated, and they also involve networking, talking to other computers. But this one machine does these many tasks, and it's selected by the software. And that's one of the great economic savings that's enabled by the computer. Importantly, this hardware can even do things that sort of weren't invented when you actually deployed the hardware. And this facilitates fast change. So the version of Zoom you're using right now probably didn't exist when you bought your computer. But in a more extreme way, when America Online and others in the 90s developed dial-in email, the computers were already there for word processing and spreadsheets, and they let email spread. And for the same reason, the web spread really quickly. So this one machine can do many things, including things not yet invented. And that's one of the reasons computing has changed our world. What about going forward? Well, there's a lot more change coming, okay? Those of you nerds like me are fans of Star Trek. And this is a picture of a holodeck, which is virtual reality. Virtual reality, you think is about gamers and shooting themselves up. It's going to be a big deal. It's going to allow us to immerse in things in a fundamental way. I mean, we disparage television, but television allows us to reach out to the world in a way that was much more difficult before it was invented. Virtual reality is going to take that into literally 3 dimensions. It's a big deal, requires a lot of computing. Augmented reality is strongly related, and that's where you take the world and you add information to it. So this shows a mocked up application in a warehouse, helping somebody see what's happening in a warehouse and what they're looking for. And you can imagine other applications that you hold up and see what bird you're looking at, and many more serious things. This too is going to be a big deal. Personalized learning. So one of the ways we teach is we give examples. And the best examples for a student are the ones that stretch them the most, but they're not so hard to break them. And so it's very personalized, but in a mass teaching situation, you can't do that personalization. Computers could potentially really help this, but we still have to figure out ways to motivate students with computerized learning. Finally, there's amazing things like self-driving vehicles. These are a classic example, and I'm going to go into more of this later, where they're overhyped in the short run, like they were predicted to happen by 2019, but they are a big deal, and I believe they're going to eventually happen. And if they don't happen completely, they're going to happen in many situations, easing our control. And that's a great thing, and I'm in favor of that as I get older. A lot of these things are enabled by this really weird picture here called a deep neural network. It's called a neural network because it's inspired by the neurons in the human neocortex, but it's evolved away from that in many ways. So you can think of this very much like the Wright brothers may have been inspired by birds and the shapes of their wings, but they soon learned that, well, when you do artificial flight, you probably don't want to flap your wings. So these changes are afoot, and how do we make them happening? And that's where CRA's Computing Consortium helps. We're trying to catalyze information technology's virtuous cycle, IT for information technology. So a simple model of our country is that we have a government, we have academia, we have industry, we have citizens, and they all talk to each other, symbolized by these very dashed lines. They talk to each other even about information technology, but we would like to make this communication more effective. So what the CCC does is it tries to catalyze and talk and get a virtuous cycle going, where government can better fund research and academia can better produce research results and students to industry, which produces better products, which makes citizens' lives better and induces them to pay more taxes. This picture is not to scale because the CCC is like 20 members, mostly professors, plus a few from industry and several staff. And what we do is pre-competitive white papers and workshops to really try to make this happen. And much of what I talk about in this talk is based on these white papers, and some of it is the background to these white papers. Okay, so I'm arguing that computing has and will change our world. Now let's look at artificial intelligence. And this has the potential to really free humans from some repetitive tasks, but there's a but. So you hear a lot of hype about artificial intelligence or AI or machine learning or ML, but what are they? Well, this blob here in the Venn diagram they're going to have, this represents artificial intelligence. So there's a bunch of stuff, a bunch of technologies that are called AI. Now, what is AI? Well, the artificial part is pretty easy to define. That means you're doing it, outside of a human. in this case, a machine. What's hard to define and people struggle with is what is intelligence? I mean, if you can do that divide algorithm, are you intelligent? We probably don't think so. So maybe you could define intelligence that you can author Hamlet. That's a definition, but I don't like that definition because I don't qualify. So it turns out that artificial intelligence and intelligence in general is hard to define. But there's an important subset that's really doing well that's easier to find. And that subset of AI is called machine learning. So these two terms can also be defined. So the machine means the computer in this case. And then there's learning. What does learning mean? Learning means you know some stuff, you do a task, you do a lot of things right, you make some errors. Then when presented with additional information, you do better. You make fewer errors. You've learned. And so we can define learning, and we can define even when machines are learning. And that's machine learning, or ML. Now there's an important subset of ML called deep learning, which relies on that neural network picture that I showed you a few times ago. And this is the thing that's really exploding now. It has made amazing progress. By the way, artificial intelligence was a grandiose term defined in 1955. And so this is a long road. Deep learning has made great progress over the last 10 years and phenomenal progress over the last 5, and we expect more. So a thing to watch out for is in the popular press, if these terms are used, they're really bandied about as synonyms. But now you're in the know, you know that they're technically different. So what is this deep learning thing that's really exploding? I'm going to attempt to explain that now. Okay, so the first phase in deep learning, which relies on deep neural networks, is training. And you do this in advance of applying things. It's just like you go to school in advance of a job. And so what you do in deep neural networks is that you get a whole bunch of examples that are labeled with the correct answer. Okay, and so it's a little hard to see here, but in the left of this picture, there's a whole bunch of handwritten 0, 1 through 9 digits. And they're written different ways, and they're all labeled so that the first row is zeros and the last row is 9s. Okay, and then what we do is somehow by magic, we train this neural network from these digits and correct answers so that it learns to give the correct output, usually. So what do we mean by that? Well, we can see what we mean by that by looking at the next phase. Okay, the next phase is inference. So this is when you've graduated from school and we're now using this thing, okay? And so we're gonna see new data. So we might see this 8 written on the zip code of an address on an envelope and say, I shouldn't say an 8, we see these bunch of dots and we ask, what is this? Well, if our neural network was trained well, it had never seen this exact pattern before, but it says, you know, I think it's an 8. Now, actually, it doesn't just say 8, it says 8 with 95% probability and some others with other probabilities. Then if it sees this, it says, hopefully in the best case, it says this is a 2. This is what deep neural networks do. And, you know, is it intelligent? It's a little hard to know. I mean, compare this with, if you happen to remember linear regression, if you took math or science, that's where there's a bunch of points and you learn the line, which is a simple function. This thing is learning a more complicated function, but is it intelligent? I don't know if it's intelligent. I might say no, but I do know it's learning. You feed it more data, it does better. Unfortunately, it takes a lot of data. I mean, tens of thousands, hundreds of thousands, sometimes millions of examples. It learns way slower than my toddler granddaughter. So even if you didn't understand that slide and I lost you, come on back, time to pay attention again. What are the implications of all of this? Okay, the good news is we learn more complicated things than we can program. So, you know, a joke is you can search now for cat videos and the system is very good at automatically recognizing and finding cats with really high probability. And that was something we couldn't really program very well. More seriously, you can recognize pedestrians, and this obviously has great value for self-driving cars. And then the final picture there is representing some issues with understanding human language, which systems are getting way better at, things like Google Translate. That's the good news. We can do things which were heretofore impossible by a machine. The bad news is we're not there yet. So first of all, things are fragile. Did you know that that is not a stop sign? A neural network was trained on many, many stop signs and then was presented with this image, and it did not recognize it as a stop sign. Why? Well, I'm guessing none of the training had white and black stickers on the stop sign, and so it didn't have the common sense to ignore them. Next problem is you can't explain the results. Now, what does that mean? So let's say I'm going to Netflix and I watched a bunch of movies and Netflix says, well, you like this movie, I bet you'd like that movie too. Well, I'm probably okay not knowing why Netflix thought I would like this other movie. But there's other situations, like if the medical system is recommending to my surgeon a certain procedure, the surgeon and I might want to know why it's recommending it. And right now, we're not good at understanding why these deep neural networks give the answers they do. And then finally, there's counterfactual things and causality. So if the system is trained on some data, like a rooster crowing and the sun coming up every morning, it has no idea, does the rooster cause the sun to come up? Does the sun cause the rooster to crow? Are they correlated? What happens if the rooster doesn't crow in the morning? Will the sun come up? None of this is known because it's just trained on whatever data it happens to have. And if there's missing data, it's a blind spot. So we have tremendous progress, and I expect more. I'm going to predict some changes, and then we're going to talk about what CCC did. So here's a graph based on some work that Moshe Vardi presented on a future of work. So it has two axes. On the x-axis is cognitive versus manual. So all jobs and other things revolve something amount of thinking and sometimes some amount of manual work with your hands. On the y-axis, somewhat independently, jobs can be very repetitive. You do the same thing, or they're very unique and creative, where you do different things every time. And so how information technology and AI is going to evolve on this is related to this spectra, or this axis. So the movie Hidden Figures was about these three women who were called computers for NASA. And these computers did a whole bunch of by-hand calculations of arithmetic. This has been totally subsumed by computers to the point that we find it absurd that these people are called computers. As evidence of this, by the way, one of my professional organizations, ACM, stands for the Association for Computing Machinery, to distinguish it from human computers. So that's totally succumbed to computing. In progress is very repetitive manual work, such as this example of an automobile factory where you do the exact same thing many times. This was a lot harder than replacing the cognitive work. On the y-axis is something where AI and machine learning are starting to have a big impact. Can we, with AI, replace professors such as myself? Well, I kind of hope not, but I'm fine with the more repetitive parts of my job getting replaced, like grading. And then finally, what about the manual unique, okay? Plumbers are relatively safe from automation, right? Because their job is manual and every crawl space is unique. And so what I'm going to argue is happening is that the repetitive stuff is going to be taken more, but it's increasingly going to be cognitive as well. And the impact for society is that it'll move humans, to the more unique and creative parts, different jobs, sometimes changing jobs individually. And what it'll do for society remains to be seen. Will there be enough new jobs once the more drudgery jobs are taken? In the Industrial Revolution, the answer ended up being yes. But as my financial advisor points out, past performance is no guarantee of future performance. So it's something we should watch for. So into this milieu, the CCC, partnering with the American Association of Artificial Intelligence, did a research roadmap a couple years ago, acknowledging the amazing success we've had so far about learning from patterns, and basically saying what we need to do is, partner this with human-like symbolic reasoning so that we can get past some of those absurd stop sign examples and make things more explanatory. And so these graphics show some of the fancy things that were discussed, and they're way beyond what I'm going to discuss in this talk, but you can look them up later. So that's what I wanted to say about AI. It's a little bit overhyped, but it can really free humans from repetitive tasks. I don't think anybody misses like the typing pools of old. And so if we get more repetitive tasks out, that's good, but there are issues. All right, so let's move on to quantum computing. This is something that's going to really enhance discovery, and I'll define what that means. But the catch is that it's someday, not immediately. So to understand quantum computing, what I'm going to do is try to explain quantum computing, and then we'll say you can forget if you didn't get the explanation, here's the implications. But first we're going to try to explain. So to explain, we first have to go back to regular computing, which in this context is called classical computing. So computers store everything as numbers. And it turns out they're binary numbers, but that doesn't matter. Intuitively, you can just think of them as regular numbers. But a binary number, one bit at any given time, can be one of tails or heads. And inside of a computer, we think of that as 0 and 1 because we're mathematical nerds. But think of this as a penny on a table. It's either going to be a tail or it's a head. There's two possibilities, but only one is realized at any given time. Now, if you had 2 bits, this shows you why you can get away with having binary numbers. You can now have 4 possibilities: tails, 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 heads, heads, tails, and heads, heads. And so this multiplies what you can represent, but at any given time, if you have 2 pennies on the table, it's only one of those 4 states. And if we have 8 bits, it turns out that's 256 values, and that's so important. We call it a byte in a computer, and it's used to represent all kinds of letters and characters and punctuation. And it turns out if you have more bits, how much you can represent goes up exponentially. So that's classical computing. So 2 bits, one of 4 possibilities. So quantum computing, what if you had this 2-bit number, and instead of being one of 4 possibilities, it was like all combinations of the 4 possibilities with some probability. It's like these 2 pennies were spinning on the table, and they were all kinds of things at once. Okay, at one time it's 10% tails, tails, 35% tails, heads, 25% heads, tails, and 30% head, heads. And you look at me and say, Mark, what are you thinking? This is bizarre. That it would be bizarre and counterintuitive if 2 bits could be all of this with some probability. Well, the feature is that quantum mechanics is bizarre and intuitive. It happens at time scales and space scales that are way different than where our common sense developed. And so it's allowed to be bizarre and counterintuitive. So what is quantum computing? So quantum computing relies on something called qubits, which is just an abbreviation for quantum bit. So until you look at the qubit carefully, or called measure it, it can be all values from 0 to 1. Okay, and so you can think of it as like a globe where the North Pole represents 1 and the South Pole represents 0. But while it's active, you could really be at all latitudes and longitudes at once. So you're at some probability you're anywhere on the surface of the globe. Okay, and you look at me, that is bizarre. Okay, it gets more bizarre. But if you had 2 qubits, well, then it can be at all combinations of latitudes and longitudes of the 2 spheres. This is way more than 4 possibilities of classical computing. It can really represent a lot of things, but not completely accurately. This is called entangled, if you know the technical term. And this is where the power of quantum computing comes from. So this is bizarre and counterintuitive. And, so there's a limit to how much intuition I can give into it. So that's what happens with qubits. So what's this good for? So if I've totally lost you on how that quantum computing works, you can, not to worry, come back here, and I will tell you, what's good and bad about it. Okay, so what's good about it is that it's really great for a hard search for some answer where it's easy to check that you got the right answer. Okay, so what do I mean by that? So it turns out electronic commerce depends on factoring being hard. Now, you all learned factoring in school, and many of you don't remember the term, I bet. Factoring says, given a number like 15, can I find what you can multiply together to get 15? And you say, well, given 15, you multiply 3 and 5 together, and that gets 15. That's easy. So how hard can factoring be? Well, factoring gets harder for this 1,000-bit number, which turns out to be about 300-digit number. What factors do you multiply together to get this number? It turns out, as far as we know, this is very difficult. But if a quantum computer could somehow tell us, I think these are the factors, it's really easy for us to check if it got the right answer. And that's because we can just multiply the factors together, and multiplication is pretty easy. Turns out the fact that factoring hard is absolutely key to e-commerce, something, SSH and RSA, if you know what that alphabet soup means. And when factoring becomes easy, that's going to break down. And CCC is also looking into that. But this is further out because this requires really accurate quantum computers. They're much further out. In the shorter term, in 1 decade, what's more possible is using quantum computing to do very hard searches for chemicals and materials. Now, some of you might be saying, well, whoop-de-doo, why would I care about that? Well, what if one of those materials, one of those chemicals was a better fertilizer that allowed the food to grow even as climate change happened? You could use the quantum computer to search for these molecules, and then you could test in simulation and experiments whether the few candidates worked. Similarly, we could develop drugs and search for ones that had good properties, maybe even properties that were individualized to people or small populations. And finally, what if we just develop materials like made solar cells way more efficient, reducing our fossil fuel dependency? So this is the potential of quantum computing, and the potential is very high, but we're not there yet. This is a picture of a quantum computer. I think it's a Google one. It's really quite large. It's quite bizarre. You don't see a laptop screen on it. This is really, really expensive. Why is it expensive? Well, one of the reasons is that it's not likely to pay great return on investment for 10 or 20 years. And people will argue about this, and I could be wrong. Another reason expensive is really cold. Okay, it's not cold like northern Wisconsin winter cold. It's like really cold, minus 459.68 degrees Fahrenheit, or within a 100th of a degree of absolute zero. And it takes a lot of technology to cool things down to that level. The second problem with quantum computing is we don't have enough qubits, although we're making great progress. In 2006, there were 12 qubits, 2019, 53. And so it's going to take a while to get the number of qubits we need to do useful calculation. And that's because we need a lot of qubits, in part because we also can't make the qubits that reliable. So the qubit doesn't do exactly what it's supposed to, so we have to put some extra stuff to make it logically correct. Now, in conventional computers, all of memory, RAM, is checked and has errors, and we can make it much, much more reliable with 12.5% overhead. Well, in quantum computing, the overhead to correct errors is 7 times for 1 layer of check. And if that's not good enough, you need 49 times, 7 times 7. If that's not good enough, I was appalled to learn that people at this quantum computing workshop knew that 7 to the 3 was it 343 or 434? Must be 343. Okay, and then finally, we got to program these things. And programming them is really hard at this point. And let me explain by analogy. So here is a picture of computer hardware in the 1940s, and in a lot of ways, the computer hardware today. Now, as a computer hardware expert, I can actually tell you what all of this does. But if you were an expert on fertilizer or solar panels, you probably wouldn't know what this does. And it's a lot to ask for you to know what it does. And really, programming quantum computing is somewhat like specifying hardware at this really low level. What we need to be able is to let the people who program it think at a much higher level. And in fact, in this case, all this thing is doing is A plus B, 8-bit big. And so a programmer saying A plus B, it's a much simpler thing than doing this. And we need the equivalent for quantum computing. Quantum computing is like stuck in the 1940s for classical computing, and we need the revolution of the 1950s and 60s. And CCC promoted that in a workshop. Okay, so both of these technologies and a number of other suffer from something called the Gartner hype cycle. So Gartner is a consulting group that does a lot of analysis for business, and they identified this, and I'm going to take a little time to explain it. So on the y-axis is expectations, how excited people are with a technology, okay? And then on the x-axis is time. So the first thing that happens with a new technology is somebody innovates, they come up with the idea, they do a little bit of work. And then within a year or two, there are this peak of inflated expectations. This is going to change the world in no time. Think self-driving cars. Okay, and then it doesn't come as fast as you would think, or people thought. And you enter the trough of disillusionment. Like, well, the self-driving cars didn't work. They're probably never going to work. Okay, and then comes the slope of enlightenment and a plateau of productivity. If things actually work, it takes much longer than you think. And so it seems like a truism of humans is that we have this overconfidence in technology change in the short run and an underappreciation of its profound impact in the long run. That's captured by this Gartner hype cycle. Now, this is the one from 2018. What you can't see, it's probably too small, but deep neural networks are right there at the top, and quantum computing is scaling right up on the thing. So what happened 2 years later? Well, 2 years later, in 2020, AI has expanded so that it's in many places. I'm exploiting to explainable AI that's right there. And quantum computing isn't even there, because I think what people found is that the hype was, it's way further out. Okay, so beware this hype cycle whenever you see a new technology. It's definitely true for AI and quantum computing and many other things. All right, so let me close here with computing and society. Computers are amoral. They're neither moral or immoral. That's humans' job to hopefully be moral. So let's look at computing and some questions. So do we want computing for better solar panels, more efficient supply chains that save money for producers and consumers, and remote communication like Zoom, which has made this pandemic better? Sure. Okay, but what about, do we want facial recognition of terrorists or citizens? Turns out if you're going to look for terrorists, they're sufficiently rare that many other citizens will be identified. Do we want this technology for recommending a movie? Sure. Surgery? Maybe not. What about predicting human behavior? There's a classic case where technology was used to predict whether, based on a whole bunch of data, whether after parole people were likely to return to prison or not. And you know what? It showed that black men were most likely to return to prison. What was the problem? The problem is that it was trained, it faithfully examined the data, which contained bias from the original humans that made the decisions. And this persisted even when race was removed as an explicit parameter, because the blackness was correlated to other things. How do we correct for this? Should we correct for this? Let's look at one example in an oversimplified way. Fairness. Fairness is even hard to mathematically define. Which is fair? Is the left picture fair, where everybody gets an equal boost? Is the right picture fair, where everybody gets a boost sufficient to get to the same level? Does the answer change whether the context is employment, education, or accessibility? And, you know, the CCC worked on this, and we have a workshop. And in the next slide, I'll present some results, but I have to say the results are really questions, not answers. And, you know, you might say, what's new about this? You know, automatic credit scoring is like a half century old. And so what's the difference? Well, what's new is scale. You can err 1,000,000 times rather than several. Ubiquity. The credit score, for example, is used way beyond its original purpose. Its purpose was whether you qualify for loans and credit cards, but it gets used for whether you should be hired as an employee, and I've heard instances of it being used for prospective mates. Accountability, especially with deep neural networks, how do you explain or make appeals? And so really more questions than answers. And I won't go into all of these here, but, you know, factors that a person can or cannot control. You allegedly can control how hard you work. You cannot control the color of your skin. How do you take that into account? What if the training data has unfair bias, like that example I gave on the parole data? And how, if we don't trust computing completely, which I'm skeptical that we should, how do we work symbiotically with the human deciders? Big questions. So going forward, in my judgment, computing professionals need to learn more about ethics and other viewpoints. We need to learn ourselves, and we need to work with other disciplines. We also need to build in mechanisms to implement policies. So what is this mechanism and policy stuff? So if you take the Federal Reserve, for example, it could have a policy of wanting to keep low inflation or keep high employment. And then a mechanism it might apply is the discount rate that it loans to other banks. So in computing, we have a similar thing. The EU put out this policy of the right to be forgotten, and then the computing companies had difficulty because they didn't have the mechanisms to even implement this. So an example of the right to be forgotten is like an arrest record that didn't lead to a conviction, or a naked video that was old enough. And, you know, not all things are easily implemented. So we need to work together with people on this. We also need to be a resource for citizens and government on like what's possible, and get influence on what we should change to make possible. You're not off the hook either. Society must remember that computers are amoral, lacking a moral sense, unconcerned with the rightness or wrongness. We humans should aspire to be moral and immoral, and we can do this with computing as a tool. So shall we? Now, before we switch to questions and answers, let me just hit you with a few fun quotes. All computers do is fetch and shuffle numbers, but they do it fast enough that the results appear magic. Steve Jobs. This is completely true. I think, therefore I am. Descartes. It will be interesting when we want to apply this to machine learning. God does not play dice with the universe. Einstein regarding quantum physics. Turns out the great man was wrong in this case. Quantum physics totally relies on probabilities. And finally, any sufficiently advanced technology is indistinguishable from magic, by the science fiction writer Arthur C. Clarke. I think our technology is magic. I remember several years ago being struck doing a video call from Haifa, Israel to my wife in Madison, Wisconsin for no charge to myself. That was magic. And can you imagine how different the 1918 pandemic would have been if people even knew they were supposed to social distance so much? We would have been left with much fewer communication means than today. So with that, we can segue into question and answer time. And so what I'm going to do is two things. I am going to stop sharing, and I'm going to end recording, if I actually remembered to start recording. Yes, I did. So we're going to